Okay, welcome to Math200, Calculus number 1. I am your instructor, Russ Frith. The class lecture notes are found on the class website, and here's the URL for the class website. On this website, you'll find WebAssign key code, WebAssign assignments and their due dates, and of course as well as the syllabus, which shows the schedule of exams. If you have any questions, feel free to contact me or email me. Okay, so this is lecture number 1. Let's see, lecture number 1 will consist of review of topics from algebra and trigonometry. If you go to the class website, or actually not the class website, excuse me, but my home page, you'll find links to my algebra and trigonometry notes, and you may want to refer to them on occasion as a reference for some of the topics that I may not have time to present in class. As we get to these topics, of course, I will point you to the reference links, and then you can do those research points at your leisure, and I don't anticipate that you would have too much difficulty accessing those and refreshing yourselves on those topics. So to begin with, we'll talk about the notion of a function. So what is a function? So a function f is a rule that assigns to each element x in a set D, often called the domain, exactly one element called f of x in a set, say, E, which is the range of the function. Now, you'll notice that for this format of using video lectures, I'm using the typewriter. I readily admit that I'm going to be making a considerable amount of typos as I type text, talk, and type text. So if you spot well, you will spot a number of errors that I make in my video notes. So if you would kindly send me an email as a reminder to correct the notes or raise the questions in our class meetings, I'll be happy to correct them. So please bear with me as I'm relatively new to this particular format for presenting the material, and I expect a few typos and other kinds of technical errors to drift into the notes, but we'll get it all straightened out as time goes on. Okay, so back on the topic of function. One of the most prominent functions that we're going to be working with in this class is, interestingly enough, the straight line. So the straight line. So as a review, I'm going to talk about some of those components of a straight line. So new page, next page. I think it's Control M for next page. I'll have to get off the text editor and go Control M. Okay, there we go. So on page 2, I'm going to insert, let's see, a browser. And I'm going to pull up some of my lecture notes on straight lines. Okay. Okay. See if it resolves. Okay, there we go. All right. Now, here we have essentially the graph of a straight line. If you notice this graph right here. And what I've got right here is an expression for the equation of a straight line in the xy plane. And this is often called the point-intercept form. Point-slope, excuse me, not point-intercept, but point-slope form. Sorry, point-intercept is another form that I'll be talking about. Point-slope. And the structure of a point-slope, as you may know, is that we're given a slope, which is calculated based on the coordinates of 2 points right here. So we have 2 points, say point A, which coordinates are x sub 1, y sub 1. Now I'm going to presume that you're familiar with the subscripted notation, the subscripts being 1 in this case for the representation of point A. And say the coordinates of point 2 would be what? X sub 2, y sub 2. And so the idea is to draw a straight line connecting the 2 points. And the length of the line, of course, is infinite. So in this particular case, x1 is -1. Let me zoom in. Oh, I have to zoom in. It'll let me. Yeah, there we go. So you can see the grid, right? So if we let x sub 1 equal -1, which is right here, and y sub 1 is 1. So here's x sub 1, here's y sub 1, and then of course here is the plotted point. Okay? And let's see if I can pan this graph. What do we have next for this particular example? We have x sub 2 equal to 3, so if I were to pan, so let's pan. Erase the content so it won't obstruct your view of the graph. So in the straight line we have x sub 2 is equal to 3 and y sub 2 is equal to 2. So y sub 2 is equal to 2. Right here. So here's y sub 2. And as you can see, they junction right here. So there's the coordinate of the point. And then you see the red line connects these 2 points on the graph. Okay? So this is the point-slope form of the representation of the equation of a straight line. So you probably are well versed in this from your algebra experience. So if we let me zoom out now. Oh, let me erase the annotations here, and let's zoom out. And so you get the bird's eye view of the line, and we can say, oh, here's an example of, say, if we vary x1 from say -10 to 10, you can see how it would change the properties of the line. What's actually going on here is, as we vary the values of x1, you can see the slope of the line is changing through all the values of the real numbers. And here you see right here the different values of the slope being populated in this slide out text box. All right. So this is the point slope format for the representation of the equation of a straight line. When we get into chapter 2, this is pretty much what we're going to be dealing with. We're not going to be dealing with not much of anything else, just using the properties of this straight line to understand properties of functions in general. Okay. All right. So All right. So pause that. Okay. So there. Okay. Now, another representation, of course, of a straight line would be the so-called slope-intercept form. So that would be y is equal to mx plus b. Okay, so this is slope-intercept. And let me get rid of the see how I dismiss this. I have to redraw that. I lost the arrow on how to dismiss the keyboard here. Okay, so let me retry this again. Let me get rid of the browser and insert another browser. Okay, and let me go back to the website. Docked back here. Okay, there we go. Let's dock it at the top. There we go. Okay, so all right, so so here's our point slope form. Let me dismiss this, and let's dismiss this. Oh, I didn't want to do that. Try it again. Try it again. Insert Internet browser, and let's put the link back in. Okay, so let's not quite ready for that one yet. Okay, so let's add item, an expression. Okay. So y is equal to what? Mx plus b is our slope-intercept form. And let's add a slider for b. Okay, so b is equal to 1. Still isn't cooperating, is it? This keyboard is not releasing. Google, let's see. Step page. All right, so with the y-intercept form, I'm not seeing the tab to dismiss the keyboard. There should be a tab here, and there is no tab. That's unusual. Okay, so here's our slope-intercept form, and if we note that in this case the equation of the line is built on the slope as well as the y-coordinate of the y-intercept. Now, I want to make a note here. Let's put in a text box. Okay, so note. When we're given the coordinates of a point, x, y, we have to identify what we mean by the coordinates of a point. And we usually call x the abscissa. That's x is the abscissa of the coordinate of a point. And y is called the ordinate, or ordinate. Okay? So when we express the equation of a line in slope-intercept form, the quantity b is the ordinate of the y-intercept. Another piece of notation that I'm going to use extensively would be abbreviations for intercepts. So I'm going to say, for the sake of clarity, let's let xi denote the x-intercept of the line. And let's let yi denote the y-intercept of the line. Okay? All right. So this would be our review of straight lines and things that we're going to be dealing with. All right. Okay, so next topic. So while we're on the topic of functions, we have other types of functions, as you're aware of. We have what are called rational functions. So rational functions. Something else that we'll be dealing with quite a bit in this class. Ratio of two polynomials. All right, say, or trig functions, or a combination, right? So basically a rational function will be delineated as using this. Y, which is equal to f of x, which is equal to a ratio of two quantities in x, right? P of x over q of x, where it's understood that q of x doesn't equal to 0. Okay, so we have this. All right, so rational functions. An example of a rational function would be, say, 1 over x plus 1. Hello. Lost my ability to type. So for instance, let's consider okay, there we go. Double click gets rid of the keyboard. All right, so let's consider y is equal to one divided by, say, x minus 1. Okay, this will be an example of a rational function. And its graph would look something like this. It's basically a hyperbola, right, with a vertical asymptote at x equals 1. So at x equals 1, you have something that looks like this. All right. So there's our vertical asymptote. Okay. Another example of a function would be the so-called polynomial functions. Say y is equal to x cubed minus 4x. Okay, and this will be shown in green. So let's zoom out on that. So the green function would be an example of a polynomial function. Okay. And then we also have examples of piecewise defined functions. So piecewise defined functions take on different characteristics on different intervals. So for instance, y is equal to, say, 1 minus x if x is less than or equal to 1. And y is equal to x squared if what? X is greater than 1. So this would be a piecewise defined function, and we will talk extensively about these as well. Then we have other cases like special functions. Special functions. The most famous special function that we'll be working with in this class would be the absolute value function. And it, of course, is defined piecewise as well. So the absolute value is defined as x if x is greater than or equal to 0. And it's equal to negative x if x is less than 0. All right, special functions. So, for instance, y is equal to absolute value of x. Okay, so what would that look like? See if we can get the graph to show up. Let me dismiss that graph. Okay. So here would be your example of absolute value, shown in red for this. Right, so there's the absolute value. Another one would be the greatest integer function. Let me see if I can get that to display. Let's see, this more as let's check. I'm not seeing the greatest int function, but we'll talk about that later. Yeah, I don't see it offhand. Y is equal to, is this it? It doesn't seem to recognize it, but we'll talk about that at the appropriate time. All right, so we've talked about linear functions, and we've talked about special functions. Oh, we still have a ways to go with other types of functions. So types of functions. So we have polynomials. So what are polynomial functions? Let's see. So an example of a polynomial function. Y, which is equal to f of x, which is equal to a sub n, x to the power of n, plus a sub n minus 1, x to the power of n minus 1, plus, and then what, the ellipsis, or ipsis, I've heard it said both ways. A sub 2, the last two terms of a generalized polynomial would be a sub 2 x squared plus a sub 1 x plus a sub naught, the constant term, right? Okay. So this is the expression for a generalized polynomial. All right. Then another class of functions we have are called power functions. And those are basically functions which are powers of x. So an example power function, of a general power function that is, would be something that looks like this. X to, say, power n, where n is an element of the set of integers, which z plus means the set of positive integers. So z plus is any integer that's not negative nor 0. Right, so these are power functions. Power functions can also be written as rational functions as well. So we could have, for instance, something like y is equal to 1 over x. Okay. Or y could equal to 1 over x to the n power. X to the n. So these are the examples of power functions. All right. Then we've already mentioned rational functions. Rational functions could be considered a ratio of two polynomials or two trig functions. And then we have our trig functions, right? Trigonometric functions. Trigonometric functions. So example of the trig functions that we'll be dealing with, or some of the trig functions that we'll be dealing with. Let's see what those are. All right, so say, for instance, y is equal to sine x, right? So red curve is shown on this graph is y equals sine x. Right? How about y equals cosine x? Okay. So y equals cosine x would be the blue curve as shown on this graph. So is there a way I can change the graphing style? Let's see here, to say polar coordinates. Yeah, so I think if we go and we put radians, show axes, and let's switch to well, let's keep it in radians, and let's use Cartesian coordinate system and projector mode. Okay, so and let's zoom out. Oops, it's kind of strange looking. It's between -5. Let's change our zoom box. Okay, so maybe this will be helpful. Zoom out. So red curve is sine x, okay, and note carefully the sine function. So it's 0 at 0, and the cosine function has an output value of 1 at x equals to 0. Okay, so what else? What are the other trig functions? Well, we have y is equal to 10x, right? So that would be shown in green on this graph. Okay, so there's the tangent function. And then y is equal to cotangent of x. That would be shown in purple on this graph. Too much zooming, right? Zoom out some more. Okay, and then there are the inverse trig functions. So y is equal to cosecant of x. That would be shown in orange on this graph. Okay, and then the sixth fundamental trig function would be y equals secant of x. All right, we'll talk a lot about these as we need them. And that curve is shown in black. So there are your 6 trigonometric functions, all shown in brilliant color. Okay, so kind of a jumbled piece of artwork there. So we'll explain more as we go on. All right, so those are the trig functions, the 6 basic trig functions. I haven't talked yet about their inverses or other properties of that, but we will as time goes on. Okay, so then the next class of functions we'll be dealing with will be the logarithmic and exponential functions. So exponential and logarithmic functions. Okay, so examples of exponential functions, as I'm sure you're aware of, would be something like y is equal to a to the x, power of x, okay, where your variable is now the exponent, right, and a is the base. So what's going on here with this particular function is a is restricted, right? A is greater than 0, and a does not equal 1 to 1. Okay, so this would be an exponential function. And of course, the more famous exponential function would be y is equal to e to the x. Okay, so we'll encounter this function a lot in this class. And then the analog of exponential functions would be logarithmic functions. So y is equal to log. Let's see if I have a ready-made function. Algebra. Do I have a log function? How about? I'm not seeing one. Okay. So y is equal to log, say, base a. Nope, not the exponent. I need the other one. I need this one. Oops, I messed that up. I have to start over. But let me edit. Okay, so log is equal to y is equal to log base a of x. So this is the logarithmic function. And so if we compare, say, well, yeah, so another example of a famous logarithmic function, if we let the base a, which is a number greater than 0 but not 1, so if we let the base be e, where e is equal to what? Approximately equal to 2.71828. Okay, so if e is equal to 2.71828, then log base e of x is often written as the natural log of x. Right? And so we have the notion that y equals e to the x and natural log of x are inverse functions. So what do we mean by inverse functions? Okay, so let's see what we mean by inverse functions. All right, so let's graph y is equal to natural log of x. Okay. So the natural log function, this is one graph I would hope that y'all know very well. If not, please memorize this. The natural log function, as you see, is asymptotic with the negative x-axis, negative y-axis, and it goes very slowly to infinity as the output as x goes to infinity. And it also has an x-intercept at y equals 1. So right here, x-intercept. Okay, so there's x-intercept. So this would be your x-intercept right there. That's how you would represent it for the natural log function. So here is the natural log function. All right. The blue curve is y equals e to the x. And if you notice, e to the x is asymptotic with the negative x-axis, and as x goes toward infinity, e to the x goes toward infinity much faster than the natural log function. Now, as I said, that these two functions, natural log of x and e to the x, are inverse functions. Never forget this idea, because we will be using this concept a lot in this class. And so what is it that makes a defining property of two inverse functions? Well, they are symmetric with respect to the line y equals x, which is shown in green here. So the blue curve is y equals e to the x. Okay, the red curve is y equals natural log of x. And the green curve is y equals e to the x, y equals x. And since the red and blue curves are inverses of each other, they are symmetric with respect to the line y equals x. So what does that mean when we say that the two curves are symmetric with respect to the line y equals x? Well, here's what we mean. If I pick a point, say on the red curve, say right here, I pick that point. Oops, let me use a red dot on the red curve for clarity's sake. So if I pick, say, this point right there, all right, and so its coordinates are x, y. Let x, y be the coordinates of that point, okay? Then, because of symmetry with respect to the y-axis, I'm sorry, with respect to y equals x, okay, if x, y is on the red curve, then y comma x is on the blue curve, okay? So that's what we mean symmetry with respect to the line y equals x. So if you have an ordered pair x, y on one curve, then the ordered pair y, x appears on the inverse counterpart of the curve, okay? So that's one concept of the inverse function. Okay. All right. Okay. So what's next? Okay. So I want to talk about, I have a lot of things I need to talk about here, but what's the next item that we need to talk about? Okay, let's talk about some concepts used to graph algebraic functions, because when we get into chapter 4 of this course, we're going to be doing almost exclusively graphing algebraic functions. So I'm going to give you a sets of rules. It's going to be a start of a rather lengthy list of things that we need to do when we draw pictures of graphs. So let's get started. So we'll start out firstly by, not rules, but procedure for graphing polynomials. All right, so with polynomials, the domain of a polynomial is equal to the set of real numbers. And a symbol that I use for the set of real numbers would be a double backboned R, like this. Okay, so that would be the set of real numbers. So that means for every point on the x-axis, you have to have an output for a polynomial. The next thing we want to do when graphing polynomials is we want to find the symmetries. Find this symmetries. So there are two types of symmetries that we essentially look for. And that first type is even symmetry. So symmetry, if I can spell it right. And this implies that the graph is symmetric with respect to the y-axis. An example would be y is equal to x squared. Okay. Even functions with even symmetry possess this property. F of x is equal to f of minus x. So for instance, if I give you y is equal to x squared, okay, which is equal to, okay, so let's write it in terms of f of x. So f of x is equal to x squared. F of negative x is equal to minus x quantity squared, which is equal to x squared. All right, so when you have this kind of relationship, the function is said to have even symmetry. All right. So what does a function with even symmetry look like? Okay, so let's see. So y is equal to x squared. All right, so here we have y is equal to x squared. And we claim that it has even symmetry, which it does. So the indicator from a graphical perspective of even symmetry is if we have say an arbitrary point on this parabola, then we would expect that its symmetric counterpart would be on the graph as well. So f of x is equal to y here. F of negative x is also equal to y. So here's an example, a graphical example of even symmetry. Okay? So maybe I just should leave that up and we'll come back to it. So one of the things we assess when we graph a function is we check its symmetry. The other type of symmetry, of course, would be odd symmetry. So odd symmetry. And that implies the graph is symmetric with respect to the origin. And the classic example of an odd symmetric function would be y is equal to x cubed. And these functions possess the property that f of negative x is equal to negative f of x. So let's prove this in the case of y equals x cubed. So if we let f of x equal to x cubed, right, then what is f of negative x equal to? Well, f of negative x is equal to the negative of x cubed, which we know is equal to negative x cubed. And you can readily tell f of negative x, right here, f of negative x is equal to the negative of f of x. Okay, and so when you see this appear in your analysis of functions, you'll know that you have symmetry with respect to the origin. Okay, so let's see what that would look like for this graph. All right, so let's plot the graph y is equal to x cubed and demonstrate its odd symmetry properties. So here's y equals x cubed. And what odd symmetry means, that say if we pick a point on the graph here, oh, by the way, this is y equals x cubed. Okay? So if we pick a point x, y on the graph, then its symmetric counterpart will be negative x, negative y. So you can leverage the concept of odd symmetry in graphing odd symmetric functions. If you know, if your analysis shows that a function has odd symmetry, all you need to do would be to draw this branch, okay, and then reflect the other branch about the origin. And the way you would reflect the other branch about the origin is you just calculate points on this branch and then negate the abscissa in the ordinate and plot the negation of the abscissa and ordinates on this branch, and you don't have any calculations to do. It's almost a no-brainer at that point. Okay, so that's one thing, a very useful utility to leverage when graphing functions, which is what a good deal of this class will be about. All right. The next thing we want to deal with when plotting polynomial functions would be to find the x and y intercepts. Okay. All right, so for instance, let's say, let me go ahead and give you a polynomial function. Let's go ahead and work with one. Say we want to graph, well, let me go ahead and use the equation editor so it'll look cleaner, so I can copy it around. So y is equal to f of x, which is equal to x cubed minus 4x. Okay, so this will be the function we'll work with. Now, so the x-intercepts, of course, occur where y is equal to 0. And y is equal to 0, you can use your favorite root finding technique to actually calculate where y is equal to 0. And those are essentially the roots of the polynomial. So in this case, if we were to factor y is equal to x times x squared minus 4, okay, and that is equal to x times x plus 2 times x minus 2, once we factor it, since it's x times a difference of 2 squares. So in this class, I'm going to assume that you're reasonably competent in factoring. If you're a little bit rusty with factoring polynomials, please refer to my algebra website or go to some online tutorials and refresh your recollections of what that is. The factorizations in this class won't be too draconian like they were, say, perhaps in an algebra class, but nevertheless, I do have an expectation that you're knowledgeable of some degree of factoring polynomials. All right, so so in finding the x-intercepts for this particular function, we just set each of the 3 factors in this polynomial equal to 0. So x is equal to 0. Okay, so that implies that what? The point 0, 0 is an x-intercept, right? And x equals -2, well, that implies that the point -2, 0 is an x-intercept. And then x equals to 2, okay, that implies that 2, 0 is an x-intercept. So this polynomial will have 3 x-intercepts that we'll show on our graph. Another thing is, okay, so those are x-intercepts. Then the y-intercepts, of course, y-intercepts are found by setting x equal to 0. So in this case, if we set x equal to 0, the output is 0, so 0, 0, the origin is a y-intercept in addition to being an x-intercept. So it has a dual role. And if we look at this function, if we go back and check the symmetry, let's do a symmetry check. Okay, so what is f of minus x? That is equal to minus x quantity cubed minus 4x, right? Plus 4x. And that is equal to minus x cubed plus 4x. And that does not equal to f of x. And that also does not equal to minus f of x. So this function, this polynomial function, will have no symmetry. Okay. No symmetry. We found the intercepts. Okay. Okay, so let's move on into the additional things we need to know when we graph polynomials. We want to analyze the infinite limits of the polynomial. By this I mean, what happens as x goes toward positive infinity, what will the output be? What happens as x goes toward negative infinity, what will the output be? So it's going to look something like this. The limit as x approaches infinity of f of x. Okay, so we want to know this. And another thing we want to know is the limit as x approaches minus infinity of f of x. So we want answers to these 2 questions. Well, in the case of this particular polynomial, as x goes toward positive infinity, this x cubed term will dominate over the negative 4x. So we can pretty much surmise that as x goes toward positive infinity, y will go toward positive infinity as well. Now, as x goes toward negative infinity, if we put a very large negative number in for x cubed, well, then that goes to a very large negative output. Again, negative x cubed, negative infinity cubed predominates over the minus 4x or plus 4 times infinity. So as x goes toward negative infinity, the output will go correspondingly toward negative infinity as well. Okay, and then the fourth topic that we want to talk about would be the table of signs. So let me mention that. Table of signs. And this tells us where the graph is above. Well, I shouldn't use the word where that's somewhat imprecise. This tells us the intervals on the x-axis where the graph is above the x-axis and where the graph is below the x-axis. Okay, so I'll show you how to construct a table of signs. To construct a table of signs, pretty simple process. We create a table. All right, so let's insert a table. Let me grab the table and move it off the lower table. This table doesn't want to move. This tool is really all right, so how do I grab the table handle without redrawing the table? Oh, this is so annoying. Well, okay, I'll just work it here then. Okay, in the table of signs, here's how you proceed. We factored the polynomial, right? As you notice here, we have 3 factors in this polynomial. So in the first column of the table that you're going to build, you'll take each of the prime factors and you'll put them in the first column. Now, if it happens that one of the prime factors is duplicated, is repeated, well, then you'll repeat it in the column here as well. So for instance, if x minus 2 were repeated 2 or 3 times or more, then you would list it for each occurrence, okay, in this column. So in the first column, list the prime factors, and then in the last cell of the first column, list your output, f of x, right? So that's the first thing you want to do. The next thing you want to do is you want to draw your x-axis. Draw an x-axis, a number line, basically. So let's draw a red number line. And we'll call this essentially an x-axis. And we're going to plot some points on the x-axis. So this bar would denote negative infinity. And, okay. And so the next intersection right here, we'll plot the smallest 0 of the linear factors, or the prime factors. So in this case, this point will denote -2 because it's a 0 of this factor right here. Okay. The next 0 happens at x equals 0. So we'll make this 0. And then the next 0 happens at 2. All right, so these are the 3 zeros of the polynomial. And then the last marking will be plus infinity right there. Okay, so this is the setup for our table of signs. Now, we need to fill in information for each of these cells, and here's how we'll deal with it. We come to this cell and we ask ourselves, if we choose a number between -infinity and -2 and plug it into this factor x, what would the sign of that number be? Well, obviously it would be a negative. And so we would write a negative there. Then we go to this cell, the second cell of the second column, and we ask the same question. Choose a number between -infinity and -2 and plug it into this prime factor. And clearly the sign of that would be negative as well. Do the same for the third cell of the second column, and it will be negative as well. So what this information tells us is that f of x, if you choose a number between -infinity and -2, f of x would be the product of 3 negative numbers. And we all know that the product of 3 negative numbers will be negative. Okay? We do the same thing for the third column. Choose a number between -2 and 0 this time. Plug it in for x, and the sign of that factor will be negative. Plug in an arbitrary number between -2 and 0 into this factor, x plus 2, and the sign of that factor will be plus. Choose an arbitrary number between -2 and 0, plug it into the factor x minus 2, and that factor will be negative. So what that tells us is that between -2 and 0, f of x is a product of 2 negative numbers and a positive number, which is a positive number. We repeat the process from 0 to 2. Choose an arbitrary number between 0 and 2, plug it in for x, and the sign is plus. Choose an arbitrary number between 0 and 2, plug it into x plus 2, the sign is plus. And if we choose a number between 0 and 2 and plug it into x minus 2, the sign of that factor would be minus. And so the product of 2 positive numbers and a negative number is negative. All right. And then finally from 2 to infinity, if we choose a number between 2 and infinity, and we plug it into each of the prime factors of the polynomial, the sign of each of those factors will be plus. And so choosing any number between 2 and infinity, the output f of x will be plus. So this is our table of signs. So what does this mean? Well, this means that on the x-axis, if we were to plot this graph, the structure of the graph would be below the x-axis. Right? If you have any content of the graph above the x-axis on this interval, then your drawing is incorrect. Between -2 and 0, your drawing needs to be above the x-axis. Between 0 and 2, you need to be below the x-axis in your graph sketch. And then between 2 and infinity, you need to be above. All right? Okay, so there you have it. Okay. All right, so with this information, we're pretty much ready to start drawing the picture of the graph. So let's go back to our x-coordinate system. Let me erase all of this. And let me delete all of this. Okay, so here's our graph. And so let's check. So y is equal to x, what is it, x cubed minus 4x and we want to graph it x less than or equal to -2. Okay, so let's see what that looks like. And we said, based on our table of signs, the graph would be below the x-axis. And also, note that as x grows very, very large, the output goes toward -infinity as well. So here's our graph for x less than -2. So let's see if we can zoom into -2. Yeah, and we can pan it. Yeah, oh, it even plots the coordinates. How nice. Okay. So panning around, we see that. Okay, so as expected from our table of signs, x less than -2, the graph is below the x-axis, as you can readily see. All right, so now let's, so the next thing that the table of signs indicated to us was that between -2 and 0, the graph is above the x-axis. All right, so let's see how that's going to work out. So I'm going to reload the drawing. Oh gosh, it reloaded the drawing. Okay. So plot it again. So it's x cubed minus 4x, where x is less than or equal to 2. All right, so we got that. Need to set y is equal to. Try it again. Y is equal to x cubed minus 4x with x less than or equal to 2. Okay. It's drawing the whole graph now, interestingly enough. All right. So as you can see, oh, that should be -2, sorry. -2 is what we're interested in. That was my mistake. Okay. So now it's blue. Okay, so here's the sketch of the graph. For x less than 2. So if I click on each of the points, you can see the points on the graph. All right, now, how about, now as we anticipated, between -2 and 0, the graph should be above the x-axis. So we have -2 less than or equal to x, less than or equal to 0. All right, so that would be the orange portion, and that's shown in orange right here. So here you see the portion of the graph drawn between 0 -2 and 0. Now, we require that the graph be above the x-axis, which it is, and it also has to connect the x-intercepts. And so the only kind of picture that can be above the x-axis and connecting those two intercepts, which I've shown in green, would be this orange-shaped curve. Okay, so now we have an issue. How do we know that this orange shape is the actual shape of the graph? In other words, how far do we know? How high up do we need to go to get to this point? Why couldn't we have drawn it more in a more stretched version? Okay, and this is what calculus is mostly about. How do we know what this peak point is? In algebra, we couldn't answer that question, and in trigonometry, we couldn't answer that question. Easily, that is. But in calculus, we can answer the question precisely. So the way we answer the question is, for now at least, is we have to build a function table. So we have to do something like this. We have to kind of estimate the coordinates of this vertex right here, which is called a local maximum. So this vertex that I'm pointing to, that is a local maximum. And the way you would estimate the coordinates, at least for now, later on when we get into derivatives, we'll be able to get the coordinates precisely, would be to kind of guess what it is. So it looks like it's going to be, maybe there's a symmetric property going on here, but that's not always going to be the case. So let's take a guess and say it's -1. So I'm going to reach for my calculator, and we're going to figure out what the output of the function is at -1. Well, before I do that, why don't we build an ordered list? So let's dance around -1. All right, so let me do that. Let's go around either side. We know it's going to be in the neighborhood in some interval where -1 is, perhaps where -1 is located, just from eyeballing the graph, okay? So let's say -1.2. Let me go further out than that, just for safety's sake. Say -1.4. All right, so -1.3. -1.2. -1.1. -1. -0.9. -0.8. Okay, so let's calculate the output of these different values of f of x. Okay, so -1.4, where does f of x? F of -1.4. 1.4 negative quantity cubed minus 4 times. So that would be 2.856. And I urge you to check my math, because I invariably make computational mistakes. All right, let's try with -1.3. So that's 3. Let's try -1.2. That's 3.072. Okay. Let's try -1.1. That's 3.069. Let's try -1. Well, that would just be 3. And let's try negative 0.9. That would be 2.871. All right, so I think we've got enough information here to kind of guess where this local maximum occurs. And here's how. Can you see from the table what's going on here? We can see that as we approach, say, negative 1.2, the numbers are getting bigger. Okay, so if we're to the left, let's plot negative 1.2 here. Let me see if I can zoom in without. Can I focus on the graph? I need to get on my cursor. Why does that keep showing up? Okay, yeah, so there we go. And let me pan. Okay. So, .25, let's see, so 1 would be right here, right? So here is 1. There's 1. And notice that the largest value, this little vertex thing, doesn't occur at x equals 1. Okay, so it actually occurs, say, somewhere around negative 1.2. So this is 1. Let's see, where's 1.5? This is 1.5. And so 1.2 is right about there. Okay, so this output is negative 1.2 and say 3.072. Okay, so that would be an example of a local maximal point. It doesn't occur at the midpoint of this interval, which I think oftentimes students make that mistake. This graph doesn't have any symmetry on the interval 0 to negative 2, so be careful of that. There's a concept here that's important, another takeaway, and before I proceed further with the analysis of this graph, I want to introduce the concept of increasing and decreasing functions. So let me go ahead and write that down. So a function is increasing on an interval on the x-axis when so let me just specify. Okay, a function is increasing on an interval, x1 comma x2. Okay, so a function is increasing on this interval when f of x2, x of 2, is greater than or equal to f of x1 for x2 greater than x1. Let's see. I should say for any x2 greater than x1 on the interval x2. Okay, so what I'm saying here is if we consider the interval of this graph negative 2 to 0, all right, so let's consider this interval negative 2 to 0. Now, as we go from negative 2 to 0 in this direction, okay, up until we get to this vertex point, we see that as x increases, okay, the output value is correspondingly increasing. So you choose any x2 bigger than x1 on from negative 2 to say negative 1.2, then f of x2 will be greater than or equal to f of x1. And so we say that this function is increasing, denote it like this. This is the symbol for increasing on the interval. Okay? So we have, that's the notion of an increasing function. All right, now, likewise, we can describe what a decreasing function is on an interval. Okay, so a function is decreasing on an interval x1 to x2 when f of x2 is less than or equal to f of x1 for any x2 greater than x1 on the closed interval x1 to x2. All right? So we can readily see on this particular graph that as we go from our vertex, okay, as we increase in x values from -1.2 to 0, all right, what's happening to the function? The corresponding outputs are getting smaller and smaller. You see that as x increases on this blue interval, the output values get smaller and smaller. Okay, and so we say that the function is decreasing on the interval -1.2 to 0. Okay, so now that brings us to a very fundamental concept of calculus. We have this vertex right here. All right, so this vertex is called a local maximum. All right, so a local maximum. Let me type it in instead of handwriting it. So let's talk about a local maximum. A local maximum occurs at a point when the graph transitions from increasing to decreasing. At the local maximum, the function is neither increasing nor decreasing. Okay, so at this local max, we have the property that we're transitioning from increasing. We increase up to the local max, and then we decrease away from the local max. So this is a property of the local max. All right, so I use this opportunity to sneak in those particular concepts. In calculus, this is called the first derivative test, and we'll talk about that in Chapter 3. But I basically gave you right now a geometric argument for the first derivative test. Pretty easy to understand, pretty straightforward, I think. Okay, so there we have it. So let me erase all of this development. Now, if you refer back to your table of signs, we said that between 0 and 2, the graph of the function should be below the x-axis. Okay, so let me erase all of the typing here so I won't clutter the... Okay, so let's continue on with our graphing. Go back to cursor. So let's sketch the graph y is equal to x cubed minus 4x for x between 0 and 2. And we would anticipate that that would be below the x-axis. Let's see if that is in fact the case. So yes, as guaranteed, right here it's drawn in black. And so now we have the same concept as we had before. The dilemma left open from algebra and trigonometry is we would like to know the coordinates of this particular point, which is a local minimum, right? Okay, now we discovered that this graph has no symmetry. So it's not symmetric, or does it? Maybe it does. Let me check. Does this graph have? I do believe this graph has odd symmetry. I may have made a mistake. I'm looking at my notes now. Let's check again. What is f of negative x? Sorry guys, I made an algebraic blunder here. F of negative x is equal to negative x. Just by looking at the graph, it looks like it would have odd symmetry about the origin, right? Or symmetric with respect to the origin. So this would be, yeah. Okay, so make the correction in the notes. This function does have symmetry with respect to the origin. In other words, it has odd symmetry. All right, so go back and correct. Okay, I'll correct it on the slide in just a second. Okay, so yeah, so we do get an assist with odd symmetry. Okay, so let me erase that. So we said that the local max occurred at what? X equals negative 1.2, thereabouts. So what was the output at negative 1.2? Let me recalculate it. So negative 1.2, negative. So it was roughly 3.072. So the local max is at 3.072. Well, I guess we could use our point identifier tool to actually get it precisely. So let's see here. What is it saying? Yeah, negative 1.155 and 3.079. Okay, so if this is the local max, just using the pointing tool on the graphing tool, then we would expect that 1.155 and negative 3.079 would be the odd symmetric counterpart, which it is. Okay, so you see how the signs are flipped in the abscissa and ordinate of the odd symmetric case. Okay, so there you have it. So grab this graphic showing the local minimum. Okay, now so how do we identify a local minimum? Well, if we go here, and if we'll take note that as x ranges from, say, as x ranges from 0 to 1.155, right here, we notice that as x grows larger, f of x grows smaller and smaller, right? F of x ranges from 0 to negative 3.079. Then when we get to this local minimum point, as x grows larger away from the local minimum, the outputs start getting larger and larger. In other words, the outputs go from negative 3.079 to 0. And so this is the signature, if you will, of the presence of a local minimum. So a local minimum is identified by, a local minimum is essentially a transition point from a decreasing function, where the function is decreasing, to where the function is increasing. So if you see that kind of characteristic of the function from decreasing to increasing on an interval, then that transition point of decreasing to increasing is a local minimum. Okay, so this is a local minimum. All right, so let me go back. Well, before I move off this graph, okay, and then I'll go ahead and complete the drawing. And then the next piece of the picture would be for x greater than 2. So y is equal to x cubed minus 4x, x greater than or equal to 2. Okay, and that would be the final piece. And let's zoom out. And that would be this segment drawn in red. Okay, let me erase the clutter here. And so those are the four pieces. 1, 2, 3, yeah, the four pieces in the drawing of our graph. Also, note that as x goes toward positive infinity, the output goes toward positive infinity as well. So this is what you need to think of when you graph polynomial functions. All right, so let me go back and fix the algebraic mistake on the slide. What was it? Was it this slide? Or was it the next? It must have been this one. Okay. Okay, so I need to fix this one. Yeah, it equals to erase this. F of negative x equals to negative f of x. So f of x, I apologize for the mistake. F of x has odd symmetry. Yeah, sometimes when you go through the procedures of graphing these polynomials, they can be self-correcting. You know, you can make a mistake up front like I did with the symmetry check, but then as you plow into the table of signs and you start graphing portions of the graph, you readily see that some of your a priori calculations were wrong, and you can go back and correct it. This will inevitably happen to you as well, and so it happened to me. So it's a good learning tool. All right, I'm going to stop the first part of Lecture 1 here. We'll get into more advanced graphing techniques in our next lecture, Lecture 1, Part 2, and we'll talk about function composition and graphical transformations and inverse functions, and then we'll do some examples. So have a great day, everybody. We'll see you next lecture.